This webcast continues the discussion of the lab for energy stored in a spring, and now we're at the conclusions to finish this lab. So, elastic potential energy is energy stored as the result of the reversible, well, if I could spell, the reversible deformation of an elastic object. So, think about chewing gum or silly putty or something like that. You can deform it, but it doesn't bounce back to its original shape. Or a paper clip. You can bend it, but it doesn't bounce back to its shape. These things are deformable, but they do not store energy. In order to have elastic potential energy stored, the object has to be elastic, which means it has that property where it will bounce back to its original shape. Okay? So elastic potential energy is stored as the result of a reversible deformation. According to Hooke's law, the force required to compress or stretch the spring is proportional to the displacement of the end of the spring. We demonstrated that in figure 1 when the graph of the applied force versus the displacement had this shape. It was very linear. And so you found a relationship, and you're going to insert the physics equation that you found in step number 12 right here, right? And then the slope is a characteristic of the spring, and we found that. You wrote this up above, and also you wrote an explanation of what the slope means, right? For every additional 1 meter that the spring is displaced. So we want to put that information here in the conclusions. Then the other part of this lab, we looked at the relationship between elastic potential energy and the deformation. And the amount of elastic potential energy stored in the spring, it increased as the deformation of the spring increased, right? Here, in this graph of elastic potential energy versus the displacement, as the displacement goes away from zero in either the positive direction or the negative direction, the amount of the elastic potential energy that was stored got bigger. Okay? Here, the elastic potential energy was proportional to the square of the displacement of the end of the spring. And so we want to, let's see, that physics equation was up here at number 19. And so you will put that here in the conclusions. Okay. Then there is also a little bit of application of what we have just found in this lab. And so I've given you another set of data along with the graph of force versus displacement. And so you can find the spring constant for this is a new spring, not the one that you used in the simulation, but you're going to use 2 points from this table to calculate the slope. And that slope is the spring constant. Be careful, in this graph, displacement is given in centimeters, and you will need to convert the centimeters to meters because spring constant is always given in newtons per meter. Okay? Then explain the spring constant. That's explaining that slope for every additional. And if you don't remember how to do that, go back to step number 10 to see how to explain that spring constant. Then it wants you to calculate how much force would you have to apply to stretch the spring by 28 centimeters. And so think about what is the equation that relates the applied force to the displacement. you can go back to step 12 to find that. Be sure to use the spring constant for this spring, not the one that you used in the simulation. And also, you should probably convert this 28 centimeters to meters. Yes? And then finally, it says, okay, how much elastic potential energy is stored in the spring when it is stretched by 28 centimeters? So here you need to go back to step 21 to find that relationship. Again, use the spring constant for this spring, and again, you need to convert the 28 centimeters to meters.